Yes, class. Am I audible now? So we were
Yes,
discussing
yes.
solenoid. All right. Okay. Good evening. So Siddhika, Yaya, Rishita, Sidra, Taha. Okay. Okay. So good evening. We were discussing solenoid and toroid in the last class. Solenoid was completed. Toroid was left to be discussed. Class, what is meant by a solenoid? Solenoid was basically a device to produce magnetic field. That's what we have studied. And moreover, we had seen that in a solenoid, we have wire of copper or aluminum, mainly copper or alloy. These are turned. Fine. This structure, what we received, is called as the solenoid, right? Then we had seen the formula B is equal to mu naught Ni. N is number of turns per unit length. So you have to be very careful when you are dealing with this N. We had seen two questions on Tuesday, where one question was based upon length and number of turns separately, and the other question was this was that question, and the other question which we discussed was just having number of turns per unit length directly. So you have to be very careful when you're dealing with this question or these type of questions, because number of turns per unit length and number of turns separate and length separate can be confusing, and that will make your answer different, especially students who are appearing or who are going to appear for their entrances. They have to be very careful with that, because in your options, in your MCQs, you'll get all the 4 options correct. All right. So now let us start with toroid. So see, if I bend the solenoid into the circle by joining the two ends, this is a straight wire, this is a helical wound wire which I have. If I join the turns like this in the form of circle, so a solenoid bend in the form of circle of a closed ring is called a toroid. That's what is written, and that's what is the definition. You just have a wire, you just turn it in the form of circle, that those copper windings will give you the same thing. It's just that it's in the form of circle. Okay. Now here also we'll divide it like this in the transverse area to view it. So here again we'll get 3 sections. But here our Amperian loop won't be a rectangle like the solenoid. Yes. Why? Because this is a circle. So it's better if we take a circle as the Amperian loop. So that's what we are going to do. So first circle will be in this innermost portion, right? And then one will be a little covering from the middle, and third one will be the outermost. Now, first section and third section, these are very easy to read. Why? Because see, there is no magnetic field present. If no magnetic field is present, then straight away you will get it as 0. Right. We had seen a case in the last class when we were discussing solenoid, where the Amperian loop was taken a little outside. Yes. And when Amperian loop was taken a little outside, we'd seen that that magnetic field was 0. So our ultimate, the net magnetic, no magnetic field was existing. So there wasn't any magnetic field when you were taking an Ampere circuit. Here also, in the first region, inside this circle, a hollow empty circle is just present. Inside the circle, what will be there? Copper wire. If you take it and if you turn it, suppose this is what I have. Fine. Now within this portion, if I have like this, if you have copper turnings like this, so in this portion, in this region, you have nothing, right? So that is the centralmost portion of it. So yes, understood. So that's why in the center we have 0 magnet. Outside, there is no magnetic field outside. Yes, so 0. So first and third regions are very easy to deal with, and you have to deal with the second region. That's it, and it's very easy. The toroid portion, solenoid portions are easy. Direct questions also come. It's not difficult. Region 1, so magnetic field is 0 straight away. Integral of B dot dl will also be 0. Yes, second region, let me leave it. Third region, b is 0, so integral of b dot dl will also be 0. Easy. Now let's come to the second region. B dot dl is equal to mu naught ni. Mu naught I, but n just for the number of turns, but right now forget this n, mu naught ni. ठीक है, number of turns अभी हम 1 ले रहे हैं. We're just taking it as 1, so it's just mu naught I. So b dot dl is equal to mu naught I. Now dl is b into 2 pi r2. Now, when we are taking a single radius in the entire formula, b1 तो 0 हो गया, b3 भी 0 हो गया. Right, b1 is 0, b3 is 0. We are just left with b2. So if we are just left with b2, so is there a point of taking r1, r2, r3? Obviously, this is understood that r2 or any radius is the central radius. Is for the second region. So what you're going to do? b 2 pi r mu naught I n for a number of terms. So formula will be b is equal to mu naught n I divided by 2 pi r. This is the formula. Now net formula, net resultant, if you add all the regions, you will still get, see, 0 plus mu naught I n by 2 pi r plus 0. So net magnetic field is mu naught Ni by 2 pi r. Now class, if you just focus on this 2 pi r, 2 pi r, what is 2 pi r in terms of a circle?
DL.
Area. Yes, what is 2 pi r? Area of a circle is written as 2 pi r.
No, I
Yes,
didn't
class.
understand.
Yes, yeah.
I didn't understand the question. I didn't understand the question.
Circumference, right. So it's circumference, not area. So n by 2 pi r is the circumference. That means 2 pi r is the circumference. Circumference means length of a circle. So number of turns is n. Length of the circle is 2 pi r. Number of turns per unit length, same thing. Right?
Yes, ma'am.
So this is number of turns. This is by 2 pi r. Number of turns by 2 pi r. So this is actually the number small number of turns per unit length. It's just that for this specifically number of turns per unit length, the meaning is different. Earlier, when we had number of turns per unit length for a solenoid, it's n by L because the length is L. Now it's a circle, so n by 2 pi r. So its formula is still B is equal to mu naught n I only for both solenoid and toroid. It's just that the two meanings are different for a solenoid and for a toroid. This I'll tell you later. First, write it down. Okay, now just one graph uh, based upon this solenoid and toroid. When we are talking about the inside, that question which we have done, one long question we have done based upon the Ampere circular law. I told you that the question is also important. It comes as a derivation also, and you have to remember this one. So graph also comes from this question. So the graph comes from the inside portion. You have to write the separation. See, radius is less than a means, it is inside. And if the Amperian loop's radius is greater than the radius of the cylinder, means A is the radius of cylinder, R is Amperian. So R is greater than A means outermost part. So inside one, it is directly proportional to R radius. So it's linear graph, but it's inversely proportional in the outside region. So this is the graph which comes, and this has come a lot. That's why I've drawn this separately. So make a note point and write down and draw this graph. Then I'll start with magnetic Lorentz force. This completes with applications of Ampere circuit. See, when we are calculating the magnetic Lorentz force, so charge we take and cross product of velocity and magnetic field. All right, so you know this is QVB sine theta. All right, this is QVB sine theta. This is the magnetic force which is present. All right, electric force, you already know electric force is QE. So these are the now two forces which have come and we'll be discussing about it. The next class will also be based upon this. Now there's one note point which comes to write regarding the final and initial velocity. So this basically says that just in case if you get a condition where force is perpendicular to velocity. So see, if force is perpendicular to velocity, force will also be perpendicular to displacement because velocity is made up of displacement only. So it means your theta is 0. So work done will straight away be 0, right? In the chapter work, energy and power in class 11th, you must have studied that this is 0 when you have what? 90-degree angle, right? So 90-degree angle will make it 0. Work done, 0. Now, if we go by the work energy theorem says that work done is equal to the change in kinetic energy. And change in kinetic energy is 0. Work done is 0, change in kinetic energy is 0. Right? Work done is 0, so change in kinetic energy is 0. Means kinetic energy final minus kinetic energy initial. This is equal to 0. So you can say kinetic energy final is equal to kinetic energy initial, right? No change in kinetic energy. So what you can conclude about the work done? Half mv final square is equal to half mv initial square, half m cancelled. Final velocity is equal to initial velocity. So there was a question which said that if the it was a difficult advanced question which said that if force is perpendicular to velocity, then what will be the work, what will be the velocities of the charges flowing in magnetic and electric? So mark it important and this can come. One more thing, class. QVB sine theta, this is very common for you to write, right? QVB sine theta. So if theta is 0-degree, means they are parallel, like this, if it is if the charge particle is aligned to magnetic. So you have QVB sine 0-degree, right? So magnetic force is 0. And same thing, if it is anti-parallel, theta is 180-degree, means FB is QVB sine 180-degree. So magnetic force is 0. And if it is perpendicular, that's a lengthy case that I'll discuss later. First, write down this. Okay, class. Now the last case which was left. See, in this, we'll be using a right hand thumb rule to find out. See, what we'll do, same right hand thumb rule we have to use. Instead of current, we'll be using velocity. I've written the thing so that you can see just in case. So the way we used to put our palm to in the direction wherever we had the current flowing. Now what we'll do, we'll take up the finger towards the direction wherever velocity is present. First step says place your finger along the direction of the velocity and then curl it towards the magnetic. Now we used to curl our fingers towards the point of calculation, right? Wherever we had the point of calculation. Now what we are going to do, if we have the point of calculation, there we have the magnetic field also present. So what we'll do, we'll curl our finger towards that point, right? And now the thumb, which was giving us magnetic field initially, now this will be giving us direction of force. So same thing, you have to curl it towards the finger, towards the point, and thumb gives you the direction. This is the same rule. It's just that now fingers are pointing towards velocity, curling is occurring towards the magnetic field, and thumb is giving the direction of force. So if I give you this point, suppose this is the point, this is the charge Q. Now let us look at the direction. Suppose this is going downwards. This is velocity. Let's find out the direction of force. So charge is going downwards, right? If it is going downwards and the magnetic field is inwards, so if I curl it, then finger is pointing towards the right. So this is the direction of force. So this is the direction of the force, right? Now see, if I give another point here, this is V, this is the charge. So see, now the velocity is towards the right. So I'll have my hand like this. Magnetic field inside, so force upwards. So force in this case is upwards. Now I'm giving you 2 points. Tell me the direction quickly. This is the charge. Suppose velocity is upward. This someone answer? Yes, Mariam, can you try? Take your right hand. Tell me.
Towards the right.
Towards the right. Take your right hand. Direction towards the velocity. Magnetic field is
Towards the
inside.
left.
Yeah. Okay. So this is towards the left. Okay. So this is the charge. Suppose this is the direction of velocity. Taha, tell me the direction of force. Taha. Right hand. Take your right hand. Put it along the direction of velocity. Curl your finger inwards because magnetic field is inwards. Where is the thumb pointing? Take your right hand. Wherever is the velocity, your hand should point towards the velocity. Magnetic field is inwards. So curl your finger inwards. Where is the thumb going?
Down.
Downwards, correct. See, this is the velocity. Magnetic field is inwards. And when you have the magnetic field inwards, so you have the thumb in the downwards direction, right? So this is downwards. So all of this, if see, these were just random 4 points. If I take one more point here, one more point here, one more, all these, see, where is the force? All the forces are pointing at the center, right? Here, every point, this is pointing at the center. So if I join all the charges, all these, and make it in the form of circle. So everything, all the magnetic forces pointing towards the center. It means the centripetal force is being provided by the magnetic field. All right. So basically, what can you say about this? If the particle is perpendicular to the magnetic field, means this is the third case. 0 degrees, 180 degree. 4 cases we'll do in this. 0 degree, 180 degree, 90 degree, and one more that I'll tell later. So this is all the force. This is the centripetal force pointing towards the circle. This is the case which we have to understand. So one thing, just a small revision from your uniform circular motion, which you have done in your lower class, means class 11th only. So make a note and then write about it. So in uniform circular motion, basically along the center, the centripetal force is present. Centripetal force has two things to identify it as a centripetal force. One, it is along the radius. Second, that it is pointing towards the center. Along the radius, towards the center. These two things. Okay. Now, centripetal force is not a force. Some other forces which act along the radius towards the center, those provide us the necessary centripetal force. So here, which force is providing? Magnetic force. Now, this is just a revision. So Fc is equal to mv square by r. This is the formula. M omega square by r. Now see one more thing. If we have this, so our centripetal force is mv square by r, right? And our magnetic force is qvb. Right. So if the centripetal force is providing the magnetic field, we can equate both of these. And that will lead to a different section that we'll discuss later. But first, write down this part. Please text done class once written till here. Okay, class, you all can leave. We'll continue this in the next week. Thank you,
Okay, ma'am.
class.
Thank you.